if you've been paying attention to what's been presented in the book, they have started introducing different types of chemical reactions. There were precipitation reactions, which we spent many times arguing or talking about that here recently. We've discussed acid-base neutralization reactions. The last main type of reaction that is covered in Chapter 3 are oxidation-reduction reactions, or in general called redox. Now, you may remember in your first chemistry course that you actually talked about 5 or possibly a 6th type of chemical reaction. There was synthesis. You guys vaguely recall that? There was decomposition. There were single replacement. There were double replacement. There were combustion. Okay, and then I said a 6th, and I kind of always throw acid-base neutralizations as a special type of a double replacement, because that's essentially what's going on. And you guys are fairly comfortable with all that, right? Well, as it turns out, if you think about it, we currently have only talked about the precipitation, double replacement, and acid-base neutralization. That's because all of the other ones are redox. So usually when you study a topic more deeply, you come up with more things. In this case, we're actually reducing the number of things because we split a lot of these up into other categories, mainly for you guys to help recognize how to balance them and predict what the products were. Because if you recognize something as a single replacement, well, okay, that makes your life easier. Anyway, what occurs, or how are we going to look at redox reactions? Well, what we're going to have to do is start examining something called oxidation states. And it's really probably going to be helpful to have a textbook nearby if you don't already have one. There should be 6 over in the cabinet. And I know, well, there should be 6 in the cabinet. Okay, well, when you guys use those, please try to remember to put them back. And essentially what oxidation states refers to is, I don't know, Chapter 4. Technically, oxidation states are referring to how the electrons are being shared in covalent bonds. You may remember a similar process dealing with referring to electronegativity. Does anyone recall electronegativity? Okay. So it's similar to that idea. So basically it comes down to you have a covalent bond between 2 atoms. Which of the atoms is getting the electrons most often in that bond? I'm going to do this. It's going to come up again at another point in the year, but I'm going to do it now to start your brain start thinking that way. In the past, don't write this piece down, but we have represented a covalent bond with a single line. A single covalent bond, right? And what does that line represent? A pair of shared electrons, okay? Well, what happens is, and you guys maybe remember we got to the line by doing something like this, by drawing the 2 valence electrons that were being shared. And then we said, okay, we're going to represent those those electrons with a single line. Now, the thing is, what happens is, remember, electrons have a charge, which means they have a electric field that they kind of produce around them. So really a bond is more of a kind of a 3-dimensional thing. I've drawn an oval here, or an elongated oval, to represent 2 of those dimensions, but really it's a 3-dimensional thing. So like a hot dog or a sausage or something. Does that make any sense? But, as it turns out, in this particular case, since the atoms are exactly the same, they have the same electronegativities, the two electrons are being shared equally. Okay? However, if they were being shared unequally, so for example, if I were to draw a, let's go with a carbon-fluorine bond, and I'm just picking these because you guys are familiar with this. Remember, fluorine is the most electronegative atom. Okay? So it means the electrons are spending more time with the fluorine than they are the carbon, and therefore that field, that electric field, is going to reflect that. So what's going to happen is you're going to have something that looks more like this, where the fatter end of that represents where the electrons are spending more time. The skinnier end down here means they're spending less time over there. So if you can start thinking in those terms when we have electronegativity differences, it might make your life a little bit easier down the road. Okay, anyway, there are a set of guidelines that are on page 177 in said books, and if you can kind of share amongst each other. It looks like we have at least one book per table, which is helpful. Okay? These you need to internalize, or in other words, memorize. But hopefully we're going to do them often enough that they become internalized, and your brain's not going, okay, what's rule number 3? You're just going to go through the sequence. We're going to do this way a lot of times. So anyway, as it says there, and this is very, very true, the rules are hierarchical, meaning that if you have a conflict between two ideas, the rule that occurs first will be the one that takes precedence. You'll see how that applies here shortly. First of all, the oxidation state, and please notice, if you haven't already started doing so, make the distinction between the words atom and ion. And I know some of you are sitting here going, oh yeah, I already do that, and I can tell you right now, when I look at your quizzes and your stuff, I know that not all of you are distinguishing between atoms and ions. This is the calcium atom, whereas this is the calcium ion. You have to make a distinction. These do not exist by themselves. These can. Okay. So anyway, the oxidation state of an atom is 0. The oxidation state of a monatomic ion is equal to its charge. So, going back to the example I was saying over here, what is the oxidation state of the calcium atom? 0. What is the oxidation state of the calcium ion? +2. Okay. The sum of the oxidation states of all atoms is 0 in a molecule or formula unit. Now, you all have been using that idea when you've been writing your ionic compounds ever since you learned to do that. That was the goal of how many of each ion was to come up with a net charge of 0. You guys remember all this stuff. So, for example, what is the net charge of calcium chloride? Well, we have a compound here. What type of compound is this? Is it ionic or covalent? It's ionic. How do you know it's ionic? Because there's a metal in it. That means this is the calcium ion. What is the oxidation state or charge of the calcium ion? +2. What is the charge on each chloride, or oxidation number of each chloride? -1 each. Now, when you add all that up, what do you get? A net charge of 0. Okay. Now, if it's an ion, okay, it's going to be equal to the charge of the ion. So, for example, do I want to do that? Yeah, I'll go ahead and do that one. We're not quite ready to do this one yet. We'll come back to this one. We have to do a couple more rules before we move on. In their compounds, metals have positive oxidation states. You guys knew this. Well, okay, you have been introduced to that topic before. In their compounds, nonmetals are assigned oxidation states according to the... I don't like the way this book presents this. Fluorine always has a -1 oxidation state in its compounds unless it's the F2 molecule. Because remember, that rule takes precedence. So if fluorine is combined with anything, it's always going to be a -1 charge. Can anyone offer an explanation as to why that's true? Based on either things that we have discussed in a previous class or discussed 5 minutes ago. It's the most electronegative atom. Okay? So it's always going to have an oxidation number of -1 unless it's combined with itself. Oxygens. Now, oxygens become kind of strange. I want to see if they've mentioned it anywhere. Now, they end up talking about it towards the past that table, which carries on to the next page. So I'm just going to go ahead and do this now. Oxygen is nearly always -2, which makes sense because where is oxygen relative to fluorine on the periodic table? Yeah, I know. I don't have it over here. I don't have a good place to put this yet. Because I don't like here. Where is oxygen? Right next to fluorine. So therefore, as you remember, oxygen also has a relatively high electronegativity. So that means the electrons in any bonds are going to be also attracted to it fairly strongly. It is nearly always going to have an oxidation state of -2. There is an exception. It doesn't get covered until after this table, but anyway, the exceptions are this ion. Apparently there is absolutely zero recollection whatsoever. Oh, yes, you have. Oh, yes, you have. In fact, when you got a 100% on the polyatomic ion quiz last year, you knew this. Boom, there you go. Peroxide. So peroxides, when oxygen is part of a peroxide, well, you tell me, what is its oxidation state going to be here? -1 each. There we go. Okay, so in peroxides, you charge on, or the oxidation state of, oh yeah, there they are. The oxidation states of the oxygens are going to be -1. Okay, continuing on. You know, okay, part 5, rule number 5, basically says that, hey, all the other rules above take precedence over everything before this. So what happens is we're going to run into scenarios where other elements are going to be involved that we've never been given any information about, but they're going to be combined with other elements in which we have been given information about. So we have to deduce what they're going to be. So essentially what that's saying is Most of the other elements can have a variety of oxidation states depending on what they're combined with. Okay? So if we can keep in mind that free elements, always going to be 0. Monatomic metal ions are always going to be equal to what their charge typically is. Oxygen is going to be -2 unless it's a peroxide. Fluoride's always going to be -1. Hydrogen is also typically going to be, well, what do you guys know hydrogen to be? +1. However, there are these things called hydrides. Has anyone ever heard of a hydride before? What's that? No. IDE. Means it's a -1. Okay? You've never heard of batteries that have the word hydride in them? Metal hydride batteries, like lithium hydride? Okay, look at your batteries sometime and see what they're called. Okay? Sometimes that'll come up. So anyway, there's rare circumstances that we are going to encounter in which the hydrogen is going to have a -1. Honestly, I don't think I've seen that show up on an AP exam yet, and I've seen them since 1994. So, what's hydrogen going to be? +1. It's telling you some other things there about the group 7s and the group 6s and the group 5s, but I'm telling you right now, those are not always going to be strict. So, you'll see as we go through some examples here. So let's try a few. I've got a number of them that we're going to play with here. And what we're going to do is I'll walk through 1 or 2 with you, and then I'll cut you guys loose on a few on your own. We'll start off with something relatively easy. I guess not. I'll go ahead and throw this one up there because I said we were going to do it, and it's a good one to look at. All right. 1, 2, 3, 4, 5, 6, 7. What does that mean? Is that the end? Yeah. Oh my gosh. I'm already done with 5.